Okay, I'm going to try and make a short video about standard enthalpies of formation. We did a few of these last year, but as usual, everything's a little bit more difficult this year. When I talk about standard enthalpy of formation, first of all, I'm talking about forming something, forming a compound, a molecule, and I'm taking elements to create something new. Okay, think of a synthesis reaction. So that's what the F is. I'm forming something new. But notice it says standard as well. Standard means that I'm putting everything at the same temperature and the same pressure and the same conditions so that I can standardize it for comparison. So that's what this little degree sign is. So whenever you see this degree sign, it just means that I've created an environment where everything is comparable because it's all at the same temperature and pressure. Okay, you're already familiar, I hope you're already familiar with the change in H. That's our enthalpy. So basically, when we see this at the end of a reaction, we're talking about the change in energy that happens when I form a compound at standard conditions. Okay, that's what all that is trying to tell us. Okay, and standard state has its own definitions. We'll talk about those here in a second. But it's obviously thermodynamics change at different pressures and different temperatures. If you think about it, the energy in iron as a solid is different than energy in iron as a liquid. So temperature is obviously a big deal when it comes to energy. And as you already know, kinetic energy increases with temperature. So again, we have to just kind of standardize everything so we're comparing apples to apples. The definitions for standard state definitions is one, it has to be at exactly 1 atmosphere of pressure. Okay? If we're talking about a liquid or a solid in a reaction, say carbon solid, water liquid, we assume it is absolutely pure in standard state. If it is an aqueous solution, then we assume that it is exactly 1 molar concentration. And as I mentioned before, we talk about things in terms of temperature at 25 degrees, or approximately room temperature. Here are a couple of reactions, just as an example of what you would see for formation. Notice that I'm putting, on the left, I'm creating something on the right from elements in their standard state. So pure elements, I've got nitrogen gas, it's diatomic at 1 atmosphere and 25 degrees, and so is oxygen gas. So on this side, standard state tells me that these elements do not have let me back up. Those elements technically have energy. However, since we're talking about change in energy, we assume that they don't have any energy, that they're going to have 0 enthalpy at 1 atmosphere and 25 degrees. So forming something from 0 energy, I get an endothermic change in 34 kilojoules per mole of NO2 formed. Okay. To make methanol, CH3OH, again, I'm taking carbon solid, which is at standard state at 25 degrees and 1 atmosphere, diatomic hydrogen, diatomic oxygen, and I create something. When I create methanol from 0 enthalpy, I get an exothermic change of a negative 239 kilojoules per mole of methanol created. Now, this per mole, the reason why I'm emphasizing that is because it's important that I'm creating one of these and this energy represents 1 mole. So if you're writing a formation reaction, you need to write it in such a way that there's only 1 mole of that product so that this is valid. Okay? This comes into play with Hess's law and a couple other things. Just make sure that you're cognizant of this per mole thing that they put. Excuse me. I included this in the notes. These are some common enthalpies of formation that you may need for homework problems and example problems. But just so you see how these work, okay, I'm going to take the enthalpies of formation of the products. Okay, so I'm going to add all those up. So I'm going to take all the the formations, again, this my formations of the products. I'm going to add them all up, and then I'm going to take all of I should really memorize these. There we go. Formation of the reactants. And when I take products minus reactants, I'm going to get the change in H of the reaction itself. So if I know how much energy it took, or sorry, how much energy was released when I formed these compounds, these molecules here, and I subtracted how much energy it took to have these, to create these, right? And I subtract the two, I'm going to get the enthalpy for the overall reaction. Okay, I hope that makes sense. So what you're going to do is you're going to go into not the lab manual here. Let's see here, our textbook. Let me see, I think I've got it under here somewhere. Nope. Hang on. Here we go. All right, here is our textbook. And we are currently doing thermochemistry. So if you see over here at the side, I've got chapter 6. And I scroll down, I keep scroll down. And then I see appendix, right? And in this appendix, if you, again, look at what we've got, mathematical procedures, selected thermodynamic data. So I'm going to click on this. And what I hope you see here is the beginning of all of the enthalpy of formation. If you see that there, enthalpy of formation of all these elements, compounds, and molecules. And they list them in alphabetical order, okay? And so you're going to look up the reactions, the compounds in the reaction, and then you're going to put them into this equation. So I'm going to look up CO2, okay, and only one CO2. So I'm going to look up the enthalpy of formation of CO2, and I'm going to add it to 2 of the waters, right, and add those all up. And then I'm going to subtract all of the enthalpies of formation of the reactants. Now there's one of these that you should already know. And notice I've got 2 oxygens here. But this is 0, okay? And the reason why it's 0 is because it is an element in its standard state, and it naturally exists as a diatomic gas. So we assume that that enthalpy is 0. Okay, so then I look up all these in my book, or they're given to you, one or the other. Okay, I look these all up, like right here. That's chromium, my bad. Over here, you can find CO2 right here as a gas, so negative 393, right? And then I'm going to plug it in here, and excuse me, you should get negative 891. Okay, and again, the math is not hard. The things that tend to be common mistakes, don't forget to use your coefficients. Okay, and always use products minus reactants. The equation that you'll find on your formula sheet looks like this. The enthalpy of the reaction is equal to the sum of the products. Remember, that's what this little guy means. Sum of the products minus the sum of the reactants. Okay. There are a couple of example problems that the book gives. Again, I suggest that you practice these. Make sure that you're getting the same answers. But again, make sure you look them up and do products minus reactants. Take a second, maybe pause the video and double check to make sure that you're getting the same answers. I am. For example, problem number 11, I got negative 1,396 kilojoules. Notice I don't put the mole because it's for the reaction. Okay, 12 and 13 are the exact same way. Again, double check. I got negative 850. Yes, the decimal point is there because we're adding and subtracting. It goes to the whole number. And 13 is per gram. I went over this in class, but at the very end, you need to divide by grams or do a little bit of dimensional analysis to get that final answer. The octane is a little bit higher at negative 47.7 kilojoules per gram. Okay, all right. And that ends our video on standard enthalpy of formation. If you have any questions, please let me know. Have a good night.